All right, welcome all to this fifth lecture of the Continual Learning course offered at the University of Pisa in conjunction with ContinualAI and the AIDA Doctoral Academy. This lecture is going to be about methodologies, strategies, algorithms. I'm going to use these as synonyms after a quick introduction to what is continual learning, the main issues of continual learning, and a brief overview of the benchmarks and evaluation protocols, metrics that you can use, now we finally delve into the methodologies, the algorithms to learn continually. So the core aspects in the end of this course, and in fact, this is going to be the first part of a sequence of three different lectures about methodologies. So in this first lecture, we're going to address first an introduction to a possible categorization of the strategies of the continual learning algorithms and a brief overview of their history and how they have been developed over time. Then we're going to focus on the first category, possible category of strategies, the most effective and I would say easier strategy that you can implement based on rehash of previous knowledge and information. And then we will move, as always, to an hands-on session related to how you can train algorithms in Avalanche and how you can develop your own strategies as based mostly on plugins. This plugin system that we develop in Avalanche for maximum flexibility and compositionality. Okay, so before delving into today's topics, I wanted to ask if you had some questions related to the previous lectures. So mostly about evaluation, the metrics, or the benchmarks, anything. Do we have some question here, for example, from the in-person audience? No, at home, nothing at home. So that's great. As always, you will find an open thread on our forum in which you can ask your questions. I see here you, Rudy, that actually asked something. Thanks, Rudy. And I think that was an interesting question about, for example, curriculum learning and its relationship with the continual learning. So let's start by looking at these possible, let's say, categorizations of the continual learning strategies and algorithms mostly within the deep learning realm. As we have discussed multiple times, this is going to be mostly focused on recent deep learning advancements. So first of all, I want to clarify that there's no like a fixed and clear definition of a categorization of all the possible strategies in continual learning, as you may imagine, given also the youthness of this research topic. But there's been a few alternative categorizations with even shared ideas. So I think it is worth discussing a couple of those at least. But I want also to stress that there's no formal definition for each of those categories. So that this makes very difficult, let's say, to understand if a particular algorithm or strategy belongs to one category or another. So it really depends, let's say, on a specific view of a researcher, of a group of researchers, and how they intend, let's say, these different categories. But I think it's reasonable to assume, for example, a four-way fuzzy categorization that you can see on the right. It may be also a three-way categorization by things. But let's discuss these more in details. So for sure, there are a number of strategies that are based on the idea of regularizing learning over a new experience data while preserving the knowledge previously acquired on previously encountered data and data distributions. And all these strategies are essentially based on additional regularization loss terms that are added to the main loss, so that we are able to preserve the weights, mostly parameters that are important for the previous data distributions. So we would like to change those weights as little as possible, since they represent concepts and skills that we have acquired previously. Then a second, let's say, set of strategies are instead based on the idea of rearch knowledge. So we are allowed to have a fixed, mostly fixed, external memory in which we can store a set of representative examples that we can reuse for rearchal activities. That is, mixing those patterns mostly with the newly acquired observations and rearch the knowledge we have previously acquired on those. And so with this idea, we're talking about rearchal or replay strategies, and then another, I would say, subset or different category that is often called generative replay, just with like the idea that in this case, we do not preserve specific set of examples exactly as they are seen in the past, but we are instead interested in generating these examples over time through maybe the, let's say, creation of specific generative models, one for each distribution they would like to model, or one overall generative model that will summarize them all. And then we have a fourth category that is mostly concerned with architectural changes, topological changes in the neural architectures. For example, adding new parameters, so new connections among specifically. From 2017, we have seen like a massive increase, let's say, in the amount of proposals in this area. So they are very recent, and this is also the explanation why it's difficult still to have a clear picture on what are the different categories and where we are going. So here instead you see on the bottom left of this slide an alternative categorization that was proposed in the paper, Continual Learning Survey, Defining Forgetting Classification Tasks, where Avalanche et al. Prefer to see this, I'll say, three-way categorization split in three different categories. So the replay methods we have discussed so far already, the regularization-based methods that we have discussed as well, and then instead of architectural, let's say, set of strategy, they discuss about these parameter isolation methods that they may be related somehow, but it's quite with a different twist.
Vincenzo, there is a question.
Yep.
So Angelo asks, where would meta-learning strategies for continual learning fit in this classification?
Oh, that's a very interesting question. And we're going to discuss about, let's say, more advanced views on continual learning, relationship with other partings in the last lecture, let's say, of the course. So talking about frontiers of continual learning. But if I had to choose a particular categorization for those approaches, well, it would be difficult to generalize to all the possible continual learning and continual meta-learning approaches, but they would be definitely something that is related to regularization methods and architectural ones. Because in meta-learning, you allow yourself essentially to have essentially two models at play, one that is learning the behaviors of the underlying learning model, so you're definitely talking about specific architecture in your overall model, and also a way to regularize learning in the inner model that is actually facing the new observations and should learn from it. So that's something that we will discuss definitely at the 8th, I think, lecture in the course, right before the last lecture on the invited guests, with invited guests, I promised. Any other question? No. This is just for you guys to let you orient yourself a little more in the amount of different proposals that we have witnessed so far in the literature, but you shouldn't be constrained by these views. In fact, you should instead find your own way of seeing things and methods in this area. Actually, this would help you, I think, in creating more original and you know, strategies and think a bit out of the box. So in terms of a continual learning baseline, so we presented a couple of those very quickly to the hands-on session of the second lecture on forgetting. But I think now it's the time to actually look into them and understand them a bit better, as now we have the instruments, the tools to do so. So there are a few, I would say, at least 4 main baselines that you should know about, that are often used and referred to in many continual learning papers. So the first one, it was called naive, the fine-tuning strategy, in which what we do is just continue fine-tuning backpropagation, the optimization step on the new observations, new examples we encounter in the new experience, right? So this is why it's called naive. It's just continuing with the same maybe optimizer to fine-tune your model on the new data. And it's prone, of course, to forgetting, as we have seen. Then we have a second common baseline, that is the joint training, or often called offline strategy, that is instead something that is often used as an upper bound to our experiments. So we say, okay, with that particular model, on which we base, let's say, our experiments, and that we let, let's say, we let continue learning over time, then we are saying, well, what's the best we can do with the same model, you know, contradicting even the assumption of continual learning, that is, assuming that you have access to all the data related to all the experiences at the same time. So here, for example, if you are in a multitask setting, which for each experience you have a different task, this would be commonly referred to as a simple multitask learning approach, where we train, for example, as you can see on the image on the right, a single model with a set of shared layers and maybe a set of task-specific layers to being able to solve all these tasks together. So the twist, of course, of this, again, is that we're not encountering the data related to these tasks over time, but we are allowed to process them all together. So this is not really a continual learning strategy, it's just a way to assess the performance of your continual learning strategy, how it relates to this particular offline, let's say, upper bound. The best you can do with all the data starting from scratch. Then we have a couple more methods that I think are relevant here. Something that is not really used, but I think it is relevant as a control, let's say, baseline, in which we train a separate model, one for each experience, and we plug them together with a simple ensembling technique that is quite known in machine learning, with, I don't know, some with a sum on the predicted class, a maximum, or whatever, let's say, rule to fuse the predictions. But in the end, we have a separate model for each experience, and we use them together during inference for testing. Or final and last, maybe more common baseline is the cumulative approach, where that is indeed a continual learning strategy, because we have access to the data related to each experience just over time. But in this case, let's say the idea is just to accumulate all the data into our external memory. If you recall the definition and the formulation of a continual learning algorithm, that is allowed to maintain an external memory with some relevant patterns. Well, in this case, we store all the patterns we encountered so far, and we start again the training procedure from scratch at every time step. So of course, as you may imagine, this is very, let's say, the trade-off, accuracy and efficiency trade-off, is very unbalanced towards the performance metrics, the accuracy metrics, and this is totally unsustainable over time, since most often this means that the computation and memory overheads grow linearly with respect to the number of experiences encountered over time. So these are a few baselines that you may use in your own experiments and use cases to say that your own strategy is a good trade-off. Your continual learning strategy is a good trade-off in terms of efficiency and effectiveness with respect mostly to those baselines. Yes?
I have a question regarding the difference between joint training line and cumulative. Is the difference in the setting?
Yes, exactly. So actually, at the end of the last experience, the cumulative strategy is results should be reasonably in line with the offline strategy, right? Because at the end of the stream of experiences that you have, you should have encountered all the data related to the problem, and you have access to all of them based on this definition of the cumulative strategy. So in the end, the results should be in line with the joint training strategy that has exactly these assumptions. The only thing that the main difference here is that the cumulative strategy may be intended indeed, and not just as an upper bound, so a straight line in your accuracy, performance, and the plot, but as an actual strategy that changes over time, is able to acquire new information and model your problem continually, right? The only problem is that it's quite inefficient, right? So that's the main, and it is quite dumb, so we're just starting again from scratch, relearning things we should have learned already in the past. So there's no knowledge transfer at any time. Any question from the audience as well? Okay. Was that okay? Perfect. So there are also a couple of fundamental choices, design choices that you should be aware of when you learn and you try to prototype new continual learning strategies, algorithms. I think this is quite relevant based on the current discussions that we are having within the continual learning community. So one big question is, I am allowed to start from scratch while starting to process this stream of experiences data, or I am allowed to start from a pre-trained model? Well, this is a quite an interesting, let's say, starting question, and I think this really depends on what you're trying to solve. So the problem you're tackling, mostly if you're working within a practical, let's say, domain and trying to solve a practical problem, you may want to start from a good starting point, right? So if you're, for example, trying to distinguish objects that for a robotic domestic environment we have seen before, that it may be reasonable to start from a good, let's say, feature extractor, for example, trained on the ImageNet dataset. But at the same time, many researchers think that it would be nice to study the core computational issues of continual learning, where we don't have these, let's say, form of cheating, since many of those pre-trained models are based on the assumption of an ID, let's say, sampling of the data, right? So if you really want to study continual learning, we should also try to understand how we can build robust and general representations starting from non-ID data. So this is a relevant question you may ask yourself and you may think a bit at home. Then we have a second main question that is about the model architecture. So the model architecture and topology is actually quite orthogonal with respect to the concept of continual learning, at least theoretically. And of course, practically, this may impact on the ability to learn continually, even though this is not quite clear how, at least from the evidence we have acquired so far. So for example, if you are working within a sequence learning problem, you may want to use, I don't know, recurrent neural networks. Or if you're working with a classic vision problem, you may work with feed-forward convolutional neural networks. So, and you may use many of those strategies that we are going to discuss in this course orthogonally with respect to the specific model. But at the same time, and yes, and this is also reflected in the way we, let's say, evaluate these systems, right? So we try to understand the gap with respect to the offline maybe strategies to other baselines with respect to the, let's say, absolute value of the performance. Because of course, a model topology, a model, I don't know, with many parameters would be, for example, much more effective in solving a task than a model with less parameters. But in continual learning, we're mostly concerned about the idea of learning over time, not just solving a task the best we can. So it's just more of a methodological question, right? And so you may pay attention, let's say, to the model architecture you want to use, depending if you want to solve a task at the maximal, with maximum effectiveness, for example, or if instead you want to study the core problems of learning continuum. And yes, so here I also show in this picture quite of a common, let's say, architecture you may use in a continual learning setting. If, for example, you're allowed to have what's called a multi-head or a single head approach, implementation approach of your model. So, for example, if you have separate, fully connected layers attached, let's say, to a basic and shared model, or if instead you're just considering these different classes as belonging to a single fully connected layer that is optimized jointly. So these are different options, of course, and you know, you may leverage those choices depending on the specific context of, you know, scenario you are solving in continual learning, as well as the strategy you have in mind to actually approach to those. But in general, I wanted to stress the fact that you may need to pay attention to those architectural choices, as they may impact even heavily on the performance of your algorithms in terms of real implementation results.
There is a question.
Yep.
Well, it's more of an observation, but I think it's some point. So one might ask that the choice of starting from a pre-trained model may not be always the best one. For example, when you run strategically different tasks, starting from an unlearned network would prove better, since it won't be biased for a task it has already learned. And so it can improve generalization over the entire sequence of tasks.
Absolutely, it may make sense. I think that the idea of starting from a pre-trained model is particularly useful when you have a bit of domain knowledge related to the stream of experiences you're going to face next, right? Because if you don't have any clue about what you're going to learn, then it may make sense not to start from a biased understanding on the world, right? And so if you're solving a sequence learning task and you have a model that is trained on maybe on another domain, then it doesn't make sense maybe to leverage that kind of knowledge. But that's something that I guess it's up to you guys and how you want to solve a particular problem in CL. I just wanted to let you know that this is something that is often debated and used in CL. Okay, so in terms of historical trends of these categories, we already discussed the idea that the initial focus on deep continual learning was mostly on task incremental settings, as we had defined. So a few, like 3, 4, 5, 6, just a handful of different experiences, each corresponding to a different task with quite let's say an amount of different examples that you could process, and let's say well-defined and different, and especially where the task labels were given, both during training and inference. So for example, you may have leveraged this particular implementation, a multi-ad implementation of your model. You're saying, okay, I know that the task label and that now I'm solving that particular task. I'm learning about particular task, and so I can train a particular ad on my model to solve that particular task. And I may use the appropriate ad when I face the same task during inference when testing, right? Because I know I want to, I don't know, solve this task of distinguish dogs from cats. Okay, I can use the specific ad I've been trained my model with when I was learning about cats and dogs, right? So this is very useful to specify the behavior of your model and of your learning algorithms, also to this particular architectural, let's say, definition and choice. Of course, based on this idea, it was quite natural to start thinking and developing simple regularization and architectural approaches that would leverage, let's say, these additional supervised information from the environment, from the stream of experiences. So quite a few works were focused on trying, like, simple regularization methods, you know, tweaks and tricks to work out with L1, L2 regularization, dropout, and then we have seen from 2016 the proposal of elastic weight consolidation. We're going to discuss next lecture, and synaptic intelligence, other approaches to regularize learning, always with this idea of preserving the parameters that are very important for the previous data distribution. And then simple architectural design choices, for example, this idea of having a multi-ad system or normalizing these weights to make them more equiparable over time, and this idea of freezing part of the network, adding new parts, new weights over time. So these were quite let's say, intuitive, I would say, straightforward approaches we tested in the first days, let's say, of deep continual learning. And then we quickly realized also that replay strategies were quite effective and generally applicable to many continual learning scenarios. So that that was quite of an advantage with respect to other strategies that were mostly usable in specific task settings like task incremental settings. And so the current trend that I see is that we are seeing more and more articulated, let's say, strategies, and often starting from pre-trained models. So this idea of starting from a pre-trained model is now quite accepted. Before it was much more debated, I guess. And we are seeing now a clear trend in trying new, let's say, hybrid strategies for continual learning. So not just with a single clear specific idea that we can link to those categories we have discussed before, but more of a collection of different approaches that nicely plugged together may result in a very strong and more, let's say, general applicable strategy. And the focus nowadays is of course mostly on the robustness, so less hyperparameters to tune this strategy, more generally be applicable to many benchmarks, and possibly with a more fair evaluation and what protocols that we had discussed in the previous lecture. But I would say that even up to today, these solutions are mostly heuristics, and these are not like principled methods. We can say, okay, this is quite an advance, let's say, for example, in the optimization process and the idea of learning, but they are mostly, let's say, patches put on top of the basic, let's say, gradient descent algorithm. So personally, I'm not really satisfied with, let's say, the main results we obtained so far in CL, even though some interesting strategy are starting to take on more and more complex problems. So that's promising, but I guess more work is totally needed in this field. It is quite difficult nowadays to generalize too large set of scenarios, and especially in high-dimensional settings. So most of these strategies are tested on, let's say, permutatively, cipher, they're simple, let's say limited stream of experiences, so a dozen or maybe hundreds if you're lucky, but never, let's say, considering the real unlimited stream of experiences. And for each of those experiences, then we don't have data sets with examples that are dimensional in terms of space. So very large benchmarks such as ImageNet is used, but is not the dominant, let's say, benchmark, for example, in this area. So then if you want to discuss about really effective solutions for continual learning and things that you maybe can apply to your own problems today, what I would, let's say, normally suggest that you, a master degree student or something working not directly in machine learning, would be to use replay, even for business applications, and more complex scenarios that should really work out of the box, right? And where there's no actual involvement of continual learning experts, and they should really look over the shoulders of your own program all the time. So if you want something that is really effective and automatic and easy to apply, replay is, of course, the first thing that comes into my mind. And the replay is very generally effective, and you can see here that it's nice to see, for example, in this image in the split MNIST experiments, that if you change the amount of examples that you store into your external memory, so starting from 50, sorry, there's an overlap in the numbers here, but to 2,000 examples, if you recall, it's it's quite a low number with respect to the number of images in split MNIST, right? It's 60,000. Then you quickly see that we are able to maximize the accuracy with just these few examples. So sometimes it's like 1% to 5% of your entire training set is enough to get very high performances and quite equiparable with respect to the offline strategy. So this is nice, right? We are saying that we can, for many problems, we can approximate the ID distribution, because replay is essentially doing this. We are able to approximize the performance of an offline strategy. You can also find, so in this curve, so you can see this black square here is like the point in this curve where we don't have like quite of an additional advantage as we increase the memory size of the replay strategy. So you can find this point just testing out your system on for example, in this case on split and list on your set of experiences. And that would be the perfect, let's say, trade-off, I would say, in terms of memory consumption and overhead, computation overhead related to replay. We're going to discuss this next, focusing on replay. And once you have defined your fixed, let's say, memory size, then you can be quite confident that over time your system would be able to solve that task with efficiently, let's say, with a good trade-off in terms of continual learning. But again, this replay can be seen in let's say, sometimes as a form of cheating, because we essentially say, okay, we want to keep the main gradient descent optimization algorithm as it is, as GD, and what we're doing is just to submit to this algorithm mini batches containing also data that the algorithm has already seen before to simulate somehow an AID distribution. So this is, it's okay. I mean, we are more efficient with respect to a standard cumulative strategy we have discussed before, because we don't use all the examples, and we're really smart in the selection of the samples and other strategies we're going to see next. But at the same time, I think we can do better, right? So and we'll see in the next lectures smart, let's say, methodologies that try to go over, let's say, this idea of replay. That is still something that is not clear how it could scale in terms of long horizon, for example, of experiences, and how would that be compared, especially on high-dimensional data set, and where computation memory overheads are, let's say, can become sensitive even for replay strategies. And then at some point you may say, okay, so I've seen the curve here getting to an upper bound of the performance for MNIST, for example. So is then forgetting solved if you use replay? Well, not really. So in many cases, especially if you take a long sequence of experiences with high-dimensional data, then the gap with the offline strategy may be still very large. So, for example, in this image on the right, on this paper, Latent Replay for real-time continual learning, we are working out on a much longer sequence of experiences, around 400 experiences, with very small amount of highly correlated images, in this case, short videos collected, you recall, from Core 50. So you see just an object moving smoothly in front of the camera, 300 frames, a small video related to just one object over time. So it's very prone to forgetting because we see just examples related to one class of the 50-way classes problem we are trying to solve. And so if you use as a non-replay strategy, you're able to, for example, like CWR, AR1, we're going to discuss in the next lecture, you get to a reasonable, let's say, 55 percentage of accuracy with respect to an offline upper bound of 85. So quite a huge gap, right? But nevertheless, it's nice that we see that we're able to grow our performance over time. So it's quite an interesting point, right? So if you're allowed to process data, in a never-ending fashion, we may reach that point sooner or later. So that's cool. But at the same time, there's quite a huge gap that it's, let's say, somehow reduced if we use replay. So if you add just 1.25% of the entire training set of Core 50, and this is just 1,500 images overall, so quite a few megabytes, not much. In this case, we are able to jump, let's say, to more than 20 percent and 10% points away from the upper bound. So we are able to reduce forgetting, but there's still a gap, especially if we are considering, let's say, on the edge solutions that they don't have a lot of space and resources in terms of memory and computation. You can look more of let's say, detailed analysis in terms of running time and memory occupation directly in the paper that are listed below. So Another thing to consider is that, as we have seen before, the accuracy improvements with respect to the memory size are often logarithmic in a sense. So somehow they are saturated quickly. So after a while, you don't get any more, let's say, significant, let's say, improvements in terms of accuracy. So a bit of replay is significantly helping, but after a while, it's not helping so much anymore. And so the problem with huge, let's say, buffer size is that would you guarantee to get very near to this upper bound, maybe very inefficient. And this is for the memory side. For example, if you're working on an ImageNet, let's say, based benchmark for continual learning, just 50 images for each class, 1,000 classes of ImageNet may result in a 7 gigabytes memory consumption. It's quite enough, quite big. In some cases. And something that is often discarded for replay is that when you have all these images into your memory, you're not just impacting on the overhead in terms of memory, but also in computation, because you're essentially relearning the same thing all over again with no apparent reason, right? Because you have seen them already, you have learned already from them. So why should you, again, do multiple forward and backward passes on the same images all over again? You know, this waste is more and more apparent as the time horizons grows, because images we have seen in the first batch, first experience, are seen again and again and again for every of these 400 steps. Let's have a deeper look on replay strategies for continual learning. That, again, are something that I think you should really look for if you're trying to solve a practical problem and in a stationary environment, and also because it's the easiest, let's say, solution you may start developing your own using Avalanche. So the standard approach for replay is random replay. So what we do in this approach is to just, as we are exposed to a new set of observations and examples, just sample randomly a set of those examples to fill our fixed size random memory. Once this memory is filled with random examples extracted from the current experience data, then we need a policy to replace the examples contained in this buffer, in this external memory. And quite, let's say, common, basic, naive strategy is to just replace the examples in this memory so that you have an equal representation of the examples related to all the experiences you have encountered so far. So this is a basic approach, and you may already start thinking here. There are many different options of implementing these. This is quite a naive one. So the pseudocode on the right essentially depicts the main ideas that I explained just right now. So you start with a random memory. This is void, and then given a specific size, RM size, a number of patterns that you can store in RM. For each of the, let's say, learning experiences that you're going to face, in this case, they are called training batches, but yes, they are different experiences you face over time. Then you train the model on a shuffled union of the examples of the current experience data and the random memory. And then you understand, let's say, and define these parameter, let's say the number of example H that you should try to recover from the current experience, so that you get an equal repartition of all the examples overall. In fact, you see that is the memory size divided by the current I experience you're processing. So you're saying I want this number to be the minimal, the maximum amount of examples that coincides with, that you may use, you may have for each of the experience into the external memory. And so you select these H patterns from the current batch of data, the data set related to the current experience. And then if the memory is already full, you replace randomly these H examples. And so in the end, you operate this replacement once you have selected this example, and you have the actual buffer updated. So quite simple and also easy to implement.
There is a question.
Yep.
So Mohammed asks, how would you differentiate it from traditional policy reinforcement learning algorithms that pretty much do the same?
Yeah, absolutely. So that's quite an interesting question, because something that I like to answer often is that reinforcement learning is actually solving continual learning without knowing it, in a sense. Because in reinforcement learning, you often are subject to non-stationary environments. So these agents, especially if you have this single, let's say, agent-centric view of the world, you often encounter let's say, shift in the sample of the observations, as we discussed, like a virtual shift, or the environment is changing itself. So, for example, you are moving in a different room and you want to solve a different task, and so on and so forth. So you may have in reinforcement learning different degrees of non-stationarity, and so the reinforcement learning community is very much, let's say, trying to solve also this problem, other than the, let's say, orthogonal lack of supervision that you have in reinforcement learning. So this idea that you have sports rewards instead of direct supervised signals. So they're trying to solve all of this together, right? And they came up with a simple experience replay, it's called strategy. It's actually replay as we use it here mostly. So you start by collecting a random set of observations from the environment connected to a specific reward, and then once you're learning about a new particular, let's say, set of observations and connected rewards, you mix those with the experience replay buffer. So this is something that you may read, for example, in the standard, in the classic experiments from DeepMind, very well known in the Atari game Resolution, and it was published on Science, I believe, or Nature, I guess Nature, and it is something that without that experience replay approach, it was shown in the paper as well there, that you cannot achieve, good performances on the Atari games. So this is a fundamental building block that is developed within the strategy, and we know it's essential for learning in non-stationary environments. I guess that's the answer to the question, is that they are very much related, and in fact you may find even interesting papers discussing experience replay in RL that may be useful for continual learning more in general.
There is another one.
Yep.
So I think that there may be a slides on these further on, but do you think noise samples, even if you are randomly sampling, may corrupt performance when we do the play?
So, well, if there is too much noise, you may get to, let's say, wrong predictions and having like biased models. But if you have a reasonable amount of noise, that may be even helpful sometimes. But this is something that is not really related to continual learning, is most related to machine learning itself, right? So if you get a bit of noise, that may help maybe convergence towards better local optimum, minimum, and then maybe useful. But it really depends, I guess, on the problem you're trying to solve. Okay, thanks. Then, of course, there are many different implementation options you may consider. So I list here just a few questions so that you can think about these different relevant issues, I think, when you want to develop a continual learning replay strategy. So first thing is, I want a fixed or more of an adaptive external memory. So no one forces you to have a fixed memory. But at the same time, I think it's reasonable to assume that you have bounded, as we discussed previously, resources that you deploy to your system. So I think that it's quite reasonable to have an adaptive, let's say, external memory that would satisfy your specific needs, but within, let's say, some reasonable limits. So you cannot grow the memory unlimited over time, that's for sure. It's not reasonable. But you may think of having a fixed set of resources that you can somehow give to your algorithm, depending also on external factors you may consider. Then we have the first, let's say, main question related to the replay policy, that is the sample selection. So what kind of examples to choose from the current experience data? So not all the examples are made the same, right? So you can choose not just randomly, but also maybe cherry picking some specific examples that you think are more representative maybe to that data distributions. And this is sometimes useful, but not always. Sometimes just randomly play is a quite good approximation of the problem. Then we have also what I call the mini batch sample selection. So when you have these examples stored into the external memory, then there is a question on which kind of examples that you have stored to use into the specific mini batch during the SGD optimization. That's another question. So if I have a very big, let's say, external memory, for example, in which I store all the examples, then I may decide to use to choose from this memory specific examples that are useful for training on a specific set of data they encounter in a particular experience. And you may think of different policies to select the specific example. They help you more on solving and learning about a new set of observations. Then we have the notion of separate buffers or priority buffers, not just one single buffer, but a buffer for different time scales or different classes, different tasks, different notable distributions, and so on and so forth. So that's useful to consider. Again, this is related. You may consider different time scales to represent those, or you maybe want to have just a uniform sampling over time. And then there is an important instead policy that is the replacement policy that may be not necessarily random, as we have seen before. So you may want to discard some and make space in your memory based on specific policies. And of course, there is no clear answer to all definite answer to all these questions. And this is mostly based on empirical observations that you get from your own experiments and based on relevant evidence from the literature. And a cool overall empirical evaluation that give you some hints, advice on how to do this is still missing. And finally, I want to say that choosing, let's say, these different implementations may really depend on the scenario and problem you're solving, and is more of an engineering effort, I would say, rather than a more scientific endeavor. And in fact, many continual learning researchers, they like to stick to the random replay approach to focus on something that is more principled, more interesting, because you can always find a way to let's say improve the results based on a better policy on, for example, the sample selection strategy. Maybe useful, or maybe, I don't know, I can decide to compress the examples in a smart way, and so I get more space to fit more examples, and I can say that my strategy is working better, but at the same time, this may be more of an engineering advancement, maybe not even related to learning, right? So I can just use a compression algorithm outside of the realm of machine learning and just get better results in continual learning because I have more space in terms of examples I can store. But now let's see very quickly a few interesting and I guess important strategies that have sparked a bit of interest into the continual learning community and may be useful for you to get an idea on what you can do with replay. So one of the dumbest, let's call it that way, strategy that you can think of, it's what is called by the same authors GDUMB. That stands for Greedy, Sampler, and Dumb Learner. So the idea here, what was to just, as you can see in the image on the right, greedy select as you process this a single stream of data. You may see also related to different experiences, and to select randomly and greedily all different examples you may encounter over time. So you fill your external memory with those examples, then you can check the specific greedy sampler implemented in this paper, but I think it's not really what concerns us here. And then what GDUMB does is to just train the whole model just every time from scratch directly on the buffer. And you may say, okay, well, why the hell is this strategy doing this? So it was meant to be a control baseline for continual learning. And as you may imagine, this is not efficient in any way, right? Because it's just starting from scratch and learning directly on the buffer of stored examples. But at the same time, it was shown empirically that this strategy was more effective than some other continual learning strategies. So it shed a bit of light on, let's say, the wrongful, I would say, evaluation schemes and protocols that we have been using in some benchmarks, in a sense, because this simple and inefficient strategy may work better than more complex, I don't know, regularization architectural strategies. And so these triggered a lot of interesting and strong discussions in the CL community about let's say, the quality of the benchmarks and the evaluation schemes that we use, the metrics that we use. But of course, this is quite a dumb strategy in a sense, because we are not doing knowledge transfer in any way, right? Because we are just starting from scratch every time. And it's quite inefficient, because if you're in a quite high-dimensional problem, you know, starting again from, let's say, ImageNet, right? Starting again from scratch every time, it's quite consuming, and you need a very huge buffer to do so. But if you operate with GDAM on MNIST, then you get very high quality results without so much effort. So the point here that I want to make is that you may use GDAM as an additional baseline control strategy, and they may tell you that something is wrong about your strategy or your evaluation setting, right? Because you may check, for example, the wrong set of metrics. So, for example, the main problem of GDAM is that every time you want to evaluate its quality, you need to train the system on the buffer. So if you want to evaluate the system of every iteration, this means that you need to perform this huge training on the whole buffer every time. So this is for the metric of evaluating the system at any time, any point in time, is quite ineffective. And you may discuss about this, maybe you may think of this at home, but this is quite an interesting replay strategy that may trigger a bit of interesting talks on which to reason. Another interesting and quite known strategy for replay, and I think this is relevant to start thinking about more involved, let's say, policies for the sample selection policy, is the maximal interfered retrieval, or MIR strategy. So in this case, what we are supposed to do is to choose, let's say, the examples to put into our mini batch while learning about a particular new set of data in a smart way that is considering the examples that would be somehow more interference with respect to the current knowledge that we would like to gather. So let me state this a bit more clearly. So let's say that I'm trying to now distinguish these this set of classes, so dogs from horses. Then it makes sense to select the examples in my memory that would be that would be more impacted in terms of estimated update on my weights, on my parameters, and that will be more corrupted in terms of knowledge. This way, I may be, let's say, more able to preserve forgetting for those data distributions that these examples represent. So the strategy here is based on the idea of estimating, first of all, the update on this new set of observations, and then trying a way to find the examples in my memory that are maximally, let's say, interfered by this new acquisition of knowledge. Then based on this, select the actual examples that I want to use in my mini batch, and actually learn from this mini batch containing information but taken from the buffer and incoming batch of data, and in the end update, my model according to this protocol. So this basic, let's say, policy for selecting examples to put into the mini batch was shown in this paper to have an important advantage over, let's say, more random selection strategy. So this is just a way to tell you that you may think of smart policies that may improve based on your particular problem, even quite dramatically the final results. The problem with this strategy was it may be quite slow to do this estimation step or of the update and see let's say the loss on all the, let's say, examples contained in the memory every time I want to do an update on my model. And another interesting line of research is mostly concerned with this idea of allowing to do replay not from the input space, but from the latent space. This is quite interesting because while replay from the input space is quite inefficient and biologically implausible, replay from a latent space is more interesting both in terms of efficiency but also in terms of neuroscience grounding. So as we know that from different regions of the brains and different phases, for example, during our dreaming process or in different stages of the learning activities, there is some kind of replay in terms of neural patterns and waves and that the brain is somehow considering, and this may be quite of an interesting development for learning machines as well. In this paper, latent replay for real-time continual learning, I think that this was investigated quite in detail. So you may see for a complex state-of-the-art model like a mobile net version 1 used on a complex object recognition problem in vision, it was shown how moving this latent replay layer may impact on the accuracy memory computation trade-offs. And so essentially from this layer, we, let's say, extract different volumes of activations we may use later for replay. That's main idea. And essentially, it was nice to show that, first of all, much of the computation happens in these layers. So you spare a lot of forward and backward passes related to these layers. And at the same time, you can get quite an interesting advantage in terms of performance, because much of the forgetting happens instead in these more higher layers where parameters are less shared across different data distributions. These are more of a, in this case, class-specific discriminative features instead of low-level generative features you may extract from different computer vision problems, in this case, discerning different classes they may encounter over time. You may look at this paper more in detail, but yes, the idea here is that you're not forced to work on replay only on the whole network and starting from raw input data, but you may also think of doing replay in some subpart of the networks or in the latent space more in general. Then another quite interesting development for replay strategy is what we also discussed, being possibly a different category for replay that is called generative replay. So in this case, the main idea is that, so why should be constrained in maintaining examples we have seen, while we can learn generative models that in theory would be even better to rehash information from the past, right? Because we're not constrained to the set of examples we have actually seen in the past, where we can imagine, we can dream about possible worlds we have never seen before, and maybe still useful for the future. So while this in theory is quite amusing, in practical terms, it is quite difficult to do, because generative models are difficult to scale in terms of efficiency, but also in terms of effectiveness with high-dimensional data. And they are difficult to plug into complex continual learning and evaluation schemes where you need like this huge sequence of steps and to update these models over time. As you may know, the generative models are quite unstable, especially if you're considering GANs, generative adversarial networks, and other approaches, and it's quite difficult to update them over time. But let's see a possible approach you may have. For example, the one that was proposed in 2017 by Shi et al. Continual with deep generative replay. So in this case, let's say that you have a few tasks that you encounter over time related to each experience. So the idea is to have a couple of models instead of one. So one that is discriminative, it's called like the solver, for example, CNN, in a MNIST classic benchmark, and a generator that should be able to learn about the generation of the distributions that are encountered in all these tasks. So the idea is that, first of all, when you encounter a new set of examples on these experience, these tasks, you learn a generator that should be able to approximate the examples related to this distribution. So for example, X. You get this X prime, this is just, let's say, truthful reproduction of this example. So once you have learned the generator, you can also learn your classifier, and you're able to solve that task as well as generating the data related to that task. And as you move on, so you if, for example, you move to the second task, then what you can do is to learn a new generator for that particular task. And then once you want to update your solver to be able to solve both tasks, then what you do is to generate the data with the previous generator, the previous step, to generate the examples to the first task, and you have the data related to the second task, the real ones, so you can train your solver so that you solve both tasks. And you can move to the third and fourth step in this progression, just updating your generator on the real examples you encounter in your experience and all the examples that are generated from the previous generator. It should be able somehow to generate all the examples seen to that particular point. Another option here is, of course, to maintain a different generator for the different tasks you have seen so far. So that would improve, let's say, the quality of the examples generated, but it will be much more, let's say, much less efficient because you need to maintain all these generators into memory. While on the other hand, if you maintain a single generator, you may encounter what's called the photocopy problem. So if you do a photocopy multiple times, in the end you get, if you do it multiple times, you get to a blank picture, because as you move on, as you try to reproduce examples that are themselves reproduced, then you get to lesser and lesser quality of them. And it's quite difficult to update a single generator over time incrementally. That's another problem.
And there are a couple of questions. So the first one is from Paulo. Why not generating latent variables? Well, I guess from which then to generate something else.
So, well, this idea of generative replay may be applied to generative latent replay, right? So that naive interpretation. So if the question is instead to what, Andrea, to have variables controlling maybe the...
Yeah, the question is simply why not generating, so on the possibility to generate latent variables. So yeah, I think that's the main issue is.
I think that, yeah, so that if that's the question, then it's totally possible to do so. And there are many papers actually that are trying to do so. So there are many, let's say, this was a first paper in 2017. From that on, there's been a few, that's why it's often categorized as a different category of strategies, this idea of generative replay, because there are a lot of different strategies that may be even quite articulated and different from basic, let's say, rehearsal or replay. So that's why I think that they deserve quite of a different category. But yes, there are many different options, implementations options in which you may, for example, have branches of the generator and the solver that are the same. You may have the latent generation of some patterns, and we have done so even in a paper we are going to publish next, done by Gabriele Graffieri and the team in Unibo, and where instead we also focus on the idea of negative generative replay in the latent space, for example. So with this idea of improving generalization capability of the solver, even though the examples generated are not of an high quality if you're solving an high-dimensional problem like an ImageNet. Today, it's quite difficult to work out a generative replay strategy. They may work on ImageNet, for example.
There is another one.
Oh, yeah, sure.
So this is I think, about only latent replay, but when you replay latent examples, or configurations, I think, you can only do the backward pass on the decoder, so last layers of the network. Is this a problem?
Absolutely so. In fact, in that paper that I mentioned before, you can, you know, the possibility that is mentioned is to freeze completely the feature extractor if you have that, let's say, good enough for the problem you want to solve. That would, let's say, make sure that the representations that you store at the latent space, in the latent space, are in line with the current representation they're extracting. Over time, another option would be to slowly fine-tuning it. So with the backpop pass that is only related to the new data you're encountering. And a third option would be to just update, and we have shown in the paper that is quite effective, just update the batch renormalization layers and not the convolutional ones. That is a way also to patch things together in a more coherent form as the learning progresses. But yes, that's a relevant question. I mean, you may encounter yourself in a situation in which the feature extractor layers are changed, and so the representation you store are not quite useful anymore, or you end up with a forgetting issue. But that's quite less relevant for those layers, because those layers are most related to things that are generally available for all the examples and all the data related to all these experiences. For example, in an image recognition, object recognition case, this may be related to, I don't know, the ability to recognize edges. And this is something that may be improved over time, but it's quite independent with the specific classes we may encounter over time. So it is refreshed and is not subject so much to forgetting as different features you may find in more, let's say, abstract layers in the hierarchy. Okay, so replay, just a quick summary and next steps. Definitely, let's say, study on replay in deep continual learning is still missing, I believe. Will be quite useful, especially for practical applications. And replay, nevertheless, has been shown to be an effective strategy in CL if performance are the main objective. And replay is unlikely to be, I don't know what I wanted to say here. Well, it's unlikely to be the main computational principle at the very basic of CL and in biological learning systems. And this suggests that a better trade-off in terms of effectiveness, efficiency may be found elsewhere. And that we know that there are many improvements and implementation options that have been explored and are still open to exploration in this area. And finally, that generative latent replay constitutes a very interesting future venue and direction for research in this area, but are quite challenging at the moment due to the limited capabilities of the generative models at play. So quite difficult in machine learning in general to have like robust and effective and scalable generative models that we can use directly into plug into CL, especially if you're talking about models that may be both discriminative and generative. That's even let's say models that are invertible. That's even harder. I think we can take a 5-minute break here and then start again with the hands-on session. There will be a fast introduction to the organization and the tools that you can use for defining strategies and plugins in Avalanche, as well as how you can implement replay strategies in the same library. Okay, welcome back to the second part of the lecture that is going to be mostly about Avalanche and how you can implement your own strategy through it. And Avalanche provides popular strategies that are already implemented for you and ready to use out of the box, as well as easy mechanisms and tools to define custom strategies. So we have worked a lot with Andrea and then Antonio, mostly, who is now the principal maintainer of Avalanche, to create a system that would enable researchers to do, let's say, the fast prototyping on new algorithms and strategies in CL. So that was the fundamental goal that we were aiming for, and to make this as simple as possible, while providing a way to create strategy on the fly with maximum flexibility and compositionality. So with this idea, we designed the training module, that is the module, let's say, most related to the thing we're going to discuss now, that is based on a plugin system. So that you can define strategies mostly through plugins of usable behaviors you want to develop, and that you can plug in into a backbone of a CL strategy that would somehow put under the hood all the more technical and hardware related and less algorithmic related stuff that we still need to do with PyTorch and to make things work in real life. Pretty much of the effort recently has been to define strategies that can reproduce results from published papers. So all the strategies that you will find in Avalanche have been tested thoroughly to, let's say, meet the standards, at least of the researchers that propose these strategies. There may be art patches, but you are invited to check the, let's say, a company reproducible CL project within the ContinualAI organization that is somehow listing this effort in trying to reproduce the results, the published results for each strategy offered in Avalanche. And let's just jump right into how we can use a strategy in Avalanche to instantiation. So let's say that we want to create an instance of a replay strategy that is already available in Avalanche implemented, that we'll see in a moment. You can just import the replay class and instantiate the replay class, passing as parameters, let's say, the main model architecture, so a PyTorch model that you can define your own, an optimizer, a PyTorch optimizer, an eventual criteria, no loss function, and additional parameters that may, let's say, control the specific strategy. For example, in this case, the memory size. Then we can use this strategy in the main loop we already seen in the definition of a benchmark instance in Avalanche. So we loop over the possible experiences in the train stream, for example. And then a strategy always offers in Avalanche two main methods, the train and the evaluation method. So the train method is in charge of learning from the new data and can be directly processed an experience or a list of experiences, if you will, just for maximum flexibility, and evaluation as well. So it's able to evaluate your system on an experience, maybe a test experience, it may be a train experience, maybe anything, but maybe evaluated on a list of possible experiences. So a classic loop over the the train experiences in Avalanche may be as follows. So you define your scenario, your benchmark instance, as again using the split MNIST, for example, benchmark, classic benchmark defined for you, and then you loop over all the experiences in the train stream. Then you can well, I guess this is just without using the, oh yeah, okay, here we go. When you have defined the CL strategy, but I don't see it defined here. Well, once you have defined your CL strategy, maybe replay, for example, you just call the train method on the specific experience, and you may get as a result the dictionary related to the metrics that you may have added into these benchmarks, as we have seen with Andrea last lecture through the evaluation plugin, and then you can evaluate as well your strategy, in this case on the whole test stream, because we are interested in that particular metrics, and using the eval method offered by the same strategy. So you see, it's quite easy to create let's say an experiment in Avalanche if you use standard offered strategies already available for you. So you may define maybe your own data set in PyTorch, then use some benchmarks util software in Avalanche to create this stream of experiences, and then you may use an already defined strategy available there for you, like the replay strategy, and in a couple of an handful of lines of code, you may have your own experiments in play. So what's more interesting, I think, in the training module is that, again, we have structured the system to be a plugin based system where you can define a new strategy based on different plugins that specify just a handful of callbacks that we're going to see may specify the skeleton, let's say the operative skeleton of a general strategy in CL. And this allows us to plug and play different plugins and behaviors to compose even more complex strategies, like hybrid strategies based on the available plugins already developed. For example, in this case, we may define a replay plugin handling, let's say, all the things and then the strategy, the policies related to replay, and as well an EWC, Elastic Way Consolidation, more of a regularization plugin that we know is quite orthogonal with respect to replay. And we may plug them together in these parameter, let's say, plugins that we may pass to the base strategy, the mother of all dragons, of all strategies. And then we list all the possible plugins here, and we may have specific behaviors related to the specific plugins at play without actually adding any lines of code for this specific instantiation of an hybrid strategy. So that's quite powerful, right? So the main question we're going to address next is how to write custom strategies and custom plugins. So we're going to see next in the live notebook we're going to run in a moment. And so why it's also useful to consider this plugin system, not only because of these callback systems, is not only for the development new strategies, but also for a transparent evaluation and logging, implementation. So all the things that Andrea presented last time about the evaluation protocols and metrics in Avalanche are developed indeed as a plugin. This means that you can, focus on the specific callbacks that define your strategy, just a handful of those, specialize the behavior server strategy with respect to the naive approach, for example, and then you get for free all the metrics computed and all the logging facilities computed as plugins already in place there, so you don't need to add them explicitly as plugins. So in the end, you may define your strategy just as a couple of methods, specialization of a couple of methods, and you get all the rest for free. So the base strategy, as we'll see, is based on an articulated set of callbacks. So here I just list a few of those for the train method. For the eval method, we may have another set of callbacks. But as you may imagine, we have like a fixed set of, let's say, methods that are called at different stages during the training and the evaluation. So, for example, we offer the possibility to specialize the behavioral strategy just after the training, the start of the training, or just after the start of the training of a particular experience. Or we let you specialize the data set right before training. We let you specialize the data loader, the loss function, and so on and so forth. So you may plug and inject your code at different parts of a basic strategy, a basic continual learning strategy system. So again, you can create by difference with respect to all the boilerplate code related to a standard, let's say, naive approach, is just continuing backpropagation over the new observations. And so I think we can just move directly to the actual codes because all of this is explained there. And what we promise in the future for this module is essentially more strategies as controlled by the reproducible CL project we have at play, and new plugins available for you to directly use in your experiments, and just a better supposed with different, let's say, base strategies specialized for doing more complex things like working on a meta learning, maybe operative in a scheme, or with an unsupervised reinforcement settings that are at the moment, not really well supported by the base strategy. Okay, so let's move now to these first training notebooks that we can directly access, as always, to Google Colab. So we go, as always, to Colab directly, and we try to load from the GitHub tab the ContinualAI repositories, in this case Avalanche, and we run the actual training notebook. This is a part of a collection. It is called From Zero to Hero, and you may find directly on the Avalanche website. And I suggest you to delve in a little deeper if you want to get a comprehensive idea on what you can do with Avalanche. So let's remove, I would say, and clear all the outputs, and then I guess we can just run them all. Okay, so first thing, you can install, as always, Avalanche in Colab just with a pip command, directly installing the latest, let's say, bleeding edge version of Avalanche from GitHub. And this is something that we already discussed. And you can see here that we have available a number of possible strategies that we will also face and discuss in the next lectures. But there are more, of course, but for the sake of clarity, you can import them directly as classes contained in the avalanche.training, the main module, .strategies package. Then you can also import a couple of, let's say, pre-made available models from the avalanche.models package, like a simple NLP. And so creating a strategy is as simple as instantiating a PyTorch, simple PyTorch model, creating an optimizer, for example, just simple SGD, and using a standard criterion, always defined in PyTorch, the cross-entropy criterion, loss criterion. And then a CL strategy like the naive one, just continue backpropagation, just quite of a straightforward, let's say, implementation of a child class of the base strategy, the naive class, that takes into consideration the main three parameters, the model, optimizer, and criterion, and just add a couple more hyperparameters to tune the learning process over time. And what I want to stress here is that you don't need to have those hyperparameters fixed for all the training experiences. You may also override those through the train methods. So if you pass to the train methods, the train mini batch size, and you want a particular mini batch size for that particular experience, you may do that. Because if you look at the base strategy implementation, this is something I really recommend you to do in general if you want to use Avalanche. So you can go to the Avalanche repo. And if you look directly into the training module and strategies, you see here there is the base strategies, the main, let's say, operative skeleton, as we mentioned, of any continual learning strategy developed in Avalanche. You may also use this trick that is quite useful. I don't know if you know it, but if you write. Okay. Well, and you open the, let's say, the online IDE for, no. Okay. Punto. Oh, qua. Ah, nice. So with just the dot key, you can get to the actual IDE. But essentially, with or without it, you can directly look into the base strategy that is just a simple class in Python, nothing too fancy, that is essentially defining these different train and evaluation loops with these two main functions that it offers, and defining a few, let's say, basic attributes that you can access through your plugins that define, of course, the main optimization process, and some other state variables that you can access. For example, you know, the data loader. Of course, it changes over time, and you may use to customize your own plugins. And so I really invite you to study these more in depth. If you want to write your own custom strategy, essentially you can write, you know, even if you're not, if you don't find, let's say, the base strategy to suit your own needs. So with these callbacks implementation, you may always inherit from this strategy and create your own. So changing the order of the callbacks and do anything you want. But please also always consider the fact that if you want to have the evaluation plugin and the evaluation part and logging part of Avalanche available, you may need to call the appropriate callbacks at some points. So what we invite you to do is to just start always from the base strategy, is to add eventually, is to change eventually some callbacks as you see fit, but not to erase those. Okay, so this is something, and then another important thing that I think you should get familiar with as we move on into this course is the API doc. So you get all the examples and the tutorials that we are seeing so far here on the left side of the screen, but then if you don't want to delve into the code of Avalanche, the API doc is your friend here. So you may search directly into the bar here what you think it's you know, interesting for you, and you may get, you know, more details about that particular function, method, and work from there. Okay, so after this quick notice, see that we have just a quarter, let's say 15 minutes left for this lecture. Okay, here you see just it's the snapshot of code that we discussed before. What you have already defined your CL strategy here. Nothing different from what you already discussed in the slide. But as you may imagine, that you get the logging, the textual logging directly here, and the working as expected. Then what you can do, for example, with plugins, is to create an early stopping feature, for example. So you can really define even simple things or complex things just through our plugin system that is quite let's say flexible. So for example, early stopping in this case is allowed, let's say, to stop the training process with a particular patient. That is after, I don't know, 10 epochs in which this particular metric, on the validation accuracy on the validation stream train is not improving anymore, right? So for example, again, if you are concerned about what this patient parameter means, you can just look in the API doc for this plugin. And for example, you get to the actual definition, patient, the number of epochs to wait before stopping the train, for example. So the API doc is your friend. Okay, now we can move this around. No. Control tab. No. I don't know if it's gonna disappear. Too many tabs. Okay. Okay, then we have seen already how you can plug together different plugins. Please recall that the order here is important. So for every callback, what we do is to call the specific instantiation of that particular callback for each of the plugins indicated here in the order they appear. So if they change some internal attributes of the strategy, I don't know, for example, the early stop, or you know, some plugin may change, I don't know, the data loader or the data sets, then the second plugin will be based on those attributes. Then, okay, we discussed about the different protocols. You may look at the different stages of the train and the evaluation parts of Avalanche, maybe with more attention at home, and all the different attributes that you may manipulate in Avalanche and they're present in the base strategy. But here I just wanted to show how easy it is to implement a replay plugin from scratch in Avalanche. So you can implement a replay strategy in Avalanche just by defining two simple methods, the before training experience and the after training experience. That is quite nice, right? That you can define a replay plugin and then a strategy, because a replay strategy is just defined as the behavior of this particular plugin. So you can this reservoir sampling buffer, a particular policy to manage your buffer. So what to store and how to store it, how to select it. All these questions that we have said are important for the handling the buffer in replay. Then you can, before actually training on a particular experience, you can modify your data loader so that the next callbacks are going to use, just creating a replay data loader that is available and ready to define in Avalanche for you within this benchmark utils data loader, different data loaders that are available implemented for you. Passing to this data loader the current, let's say, data set of the current experience, possibly also adapted and changed by other parts and by other callbacks, but essentially mixing it with the current buffer, our random memory, our external memory. So this replay data loader will just try to balance, if possible, these different source of data. And so once you have your data loader, then the rest of the strategy follows a naive implementation. So you just need to specify again our behavior by difference with respect to that. And so after the training, you need to update the buffer with the with the current examples that you have into this data set to face in the future the follow-up experiences. In this case, you use this update method authored by the buffer, giving, let's say, access to all the attributes of the strategy, essentially. So you pass the strategy object just to not pass the list of all the attributes that this buffer would attain or would access to. So this is essentially what you can do in Avalanche to develop a replay plugin, and you can use it. Normally here, as I was mentioning before. So after you have defined a benchmark instance, an optimizer, a model, a criterion, then you can just instantiate a naive strategy with a replay plugin in place, indicating the fixed memory size, in this case, you want to have. And then you train and evolve on the train and the test string. Okay, well, then if you write a custom strategy, for example, the cumulative baseline may be written directly as inheriting from the base strategy and defining, specializing the train dataset adaptation callbacks. So this is a way which you can also define, let's say, the cumulative strategy is a plugin, and then use the naive strategy and the cumulative plugin. But then this is something that is up to you entirely. You may always define the strategies as a child, let's say, object with respect to the base strategy class. You may define it as a plugin. What we suggest is always try to define them as plugins, as you may reuse. I mean, people outside of your own, experiments may use the plugins for other strategies. Then, if it's not conflicting with their plugins. And so here, what it does, it is a cumulative strategy, is just simply a naive approach where we use the callback function train dataset adaptation, where we just accumulate, let's say, all the data encountered in the current experience with the data we have encountered before, using the Avalanche concat dataset, let's say, class that you may have already explored in the O2 notebooks that I suggest reading in the previous lectures, and all these features we have developed to handle data sets more coherently in Avalanche. Okay, so this was mostly related to this idea of handling custom strategies, classic strategies, and custom plugins and classic plugins in Avalanche. Then the second lecture that I'm sorry, but we cannot look over for today, given the limited time that we have, is all based on, let's say, a more in-depth analysis on how you can implement, let's say, replay strategies in Avalanche. So because we have, let's say, considered the implementation of a custom replay strategy out of the box, say, using utils and tools that are already available in Avalanche, right? That replay data loader, that specific policy for sampling and, let's say, handling the buffer. But of course, you may implement your own. There are different implementation options that are not yet available in Avalanche that you may implement based on your own needs. And here you have different examples on how you can achieve that based on these different concepts. So the idea of the data loaders that may help you define the way in which you use the buffer. So what we call the sample selection strategy for the mini batches. So how you want to create the mini batches based on the current data you have available in the experience as well as the buffer. And so from which of those different subspaces, buffers to take the data to compose your own mini batches. So this is in charge of the data loader in PyTorch, something you can define your own or just using the data developed already. And of course, you may encounter data loaders that are trying to balance in terms of classes, tasks, data distributions, different groups, all the data related to different experiences, many different options that are common in replay. And then there is a way in which we need to maintain, different utils that define a way in which you can maintain the buffers, right? So which example to select from the current memory, or from the current data set of the current experience, and offer the ability to update or replace the replacement policy, for example, the example stored in this buffer. So I invite you to check these notebooks out. It's quite simple. And I think it gives you an idea on how you can implement replay in Avalanche. Just a few, an handful of lines of code. So I think it's totally worth an investigation and a read after this lecture ends even. So do we have any questions that this time we can end possibly a few minutes before 6 p.m.? No specific questions here from the in-person audience? Okay, then thank you so much for your attention at home and here. You're invited to follow the next lecture, which again is going to take place the 9th on December, not the 8th, because the 8th is let's say vacation day here in Italy. So again, we're going to meet each other in person for those who want to attend in person, the 9th of December, same time from 4 to 6 in the same room here, Sala Seminari Est. So thank you again for your attention, and I'll see you next Thursday.